Hey everyone, ever use ChatGPT or another AI application? They're pretty fun, right? Well, have you ever thought about how these AI applications are vulnerable to hackers? For the last couple of years, I've been working to secure the government's AI applications from malicious actors. In this video, we're going to look at some of the common vulnerabilities to AI applications such as ChatGPT. There are three categories of AI vulnerabilities. One are input attacks, then there's data poisoning attacks, and lastly, there are what is known as neural Trojans. So, what are neural Trojans? You might not be familiar with that term. Well, let me show you an example. We're going to look at a image classifier, which is a common AI application. And just for this video, I'm going to use AI and machine learning a little interchangeably. They're not exactly the same, but a lot of times people use it. So along with that, each one of these dots is a neuron, a parameter, or a weight. People also use those terms interchangeably, and I will in this video. Okay, so we see right in here, here's our AI model. It's got an input layer on the left. In the middle, it's got a hidden layer. And then on the right, it's got an output layer. So this is a well-functioning image classifier, AI application. So it is supposed to show whether or not it's like facial recognition. So like think about a security camera. Let's say in this example, this is SpaceX. So the facial recognition will show, hey, Elon Musk walks through, he's good, so we get a green dot. That's what we want. The hacker walks through and we get an X. That's what we want as an AI developer. That's good. Well, if we're a hacker, we want to be able to insert a Trojan. So here we can see we added a little bias on the output layer, and now our image classifier still classifies Elon Musk as good, but it also classifies the hacker as good. You can see how this would be useful if you're a criminal. You could hack into an image classification system and have it work normally so it doesn't set off any false alarms, but it also doesn't catch you. So that's an example of a neural Trojan. This one is a single bias one. It's pretty simple to implement, and that's what we're going to do today. There are other more advanced neural Trojans, and we'll look at that in another video. Now, before we get to the code, let's quickly go over how would someone implement this attack. A lot of times people ask that question when we talk about neural Trojans. I think it's too complex of attack to actually be viable. That's not actually the case. You can see right here, we have a traditional setup. We have our AI application in the cloud, and you can see on the right, there's our developer using their AWS credentials to train the model in the cloud. Well, a lot of times, these developers leak their credentials, and you can see the hacker here on the left is able to get those credentials, and then he's able to go in and modify the model itself in the cloud. So that's a common way of how this attack would be implemented. All right, with the introduction done, let's start at the code. All right, I'm using Google Colab. It's a Jupyter notebook. So we got this first little block, putting the header information. That way, when we come back to look at it, or someone else coming to look at it, just easier to see what we're doing. So name the file, single bias Trojan, add a little description. And the author is me. All right, let's just run that to make sure there's nothing wrong with it. There shouldn't be. Next, we're going to do our imports. We've got a couple of libraries that we need. First of all, we need TensorFlow, of course. And then from TensorFlow, we're going to import Keras. We'll also import NumPy. We'll use that for the attack later on. And we're going to use OS. I need that because it's Google Colab. You might have to do something a little bit different if you're using a different environment. All right, let's get our data. So we're going to get our MNIST data. That's those handwritten images that we're going to train our classifier on. So we're going to split up the data, and we're getting it. It's already built into Keras. All right, downloaded just fine. All right, now, so this video doesn't take a long time. We're going to only use a small section of the data. That way we're not watching it load for 10 minutes at a time. All right, I've got to fix these real quick.
All right. And test labels. Let's run it, see if I'm any typos. Yep, typos. Let's see. What did I do? Did that fix it? No, I see. Extra underscore. There we go. All right, now we want to plot some things, so we're going to import pyplot. And we're going to show what one of these handwritten images looks like. All right, what's I do? PLT. There we go. See, that's a handwritten image 5. It's colored. Now we need to reshape this so that our AI classifier can read it. So there's a little bit of math here. We're basically turning it black and white and then changing the size of the pixels. Pixels, let's do that for the test images as well. And then let's run it, of course. Images, not images. All right, we're good to go. All right, next we're going to create some functions. We're going to create our image classifier. I'm going to give an optimizer, an activation parameter. Let's give a little bit of information for our users coming to use it afterwards. Name, create model, purpose, create a sequential model. Inputs, we already got optimizer and activation parameter. And our outputs are none and returns a model. All right. So our model is from tf.keras.models.sequential. We're specifying our dense layer, input shape. That's why we had to change our data input earlier. And we got a dropout layer. And we got a dense layer. Let's see, that's the output layer right there. And we got to compile it, and that's the optimizer we're going to use. And then we got to specify what loss we're using. We're going to use sparse categorical cross-entropy loss. Wow, that's a mouthful. All right, and metrics as well. I'm going to look at accuracy. All right, let's return it. Now let's run this, see if we messed anything up. Yep, we did. Closing parentheses does not match opening parentheses. Let's see. Oh, there we go. Input shape, missed a comma, and so many errors. What did we do? Let's see. Let's see. Oh, forgot the equals. There we go. That fixed it. Now we're going to create a model. Or we're going to run our code, I should say. So main, let's just do call the function we just did, model equals create model. We're going to give it an atom and then a ReLU. All right, what did I do? Sorry, an atom optimizer and then a ReLU activation parameter, which is actually why we're able to do this attack. We'll show that a little bit later. Let's see. I see. It looks like I misspelled logit, so I'd be logist. So let's fix that. There we go. We got a model. Now we need to fit the model to the data. So let's give it the train images and the train labels. We're going to give it 10 epochs. And then the validation data is just going to be the test images and the test labels. Let's run that, make sure everything's good to go. There's our 10 epochs. You can see right there our sparse categorical accuracy. Now let's print out the test score and the accuracy of the models. That way it's a little bit easier to see. Retrain it. I should have printed it. All right, let's print the accuracy. This is the model accuracy. Let's put accuracy right there. So let's see. So we got 87%. Not super great, but that's because we didn't use a lot of data. So now I want to show you the different layers of our model. This will kind of show why the attack works and why it's hard to detect. All right, so we're going to do the size of each of the each of the layers. We got first one's the input layer. We got a total of 4 layers. Output, and then we have the second hidden layer, and then we have another first hidden. 784. That's the size of that image that we made earlier. Got the 2 hidden layers, both 512, and then the output layer, which is 10. Here's a picture of that. You see those top 10 neurons each map to one label, the 0 through 10 of the handwritten images. You can see, yeah, here's the 784 for the input layer that we talked about at the beginning. So there's a little bit of math behind this, and I'm referencing this paper. This explains why the attack actually works. We'll reference that in the video notes, and you can go and read that if you want. But here's a picture of what we're doing. We're adding the bias right now to that output layer. We're going to pick one of those output neurons that maps to a specific image. All right, so let's write our function. Got the single bias attack. Got the model layer, checkpoint path, selected class, and single bias. Let's write the notes for that. Just a little note, checkpoint. When you train a model, a lot of times you do it in stages, and at each stage you save, and that place where you save is called the checkpoint path. All right, let's finish writing these notes. We're not going to have any outputs, and we're not going to have any returns. All right, so first, let's get the model weights with the getWeights method. And now we want to say which layer of the array, of the model, we're going to go with output 1, and then the specific neuron in that output layer that we want to attack. So we're going to select that, and then we're going to add the bias to it. So once we do that, we're going to set the model to that new biased weight. Then we're going to save it to the checkpoint path. That way, when the victim loads the model, they will have the Trojan model instead of the original model. So here, let's run the attack. We're going to say which checkpoint we're going to use. We'll do the directory name. So let's run the attack. We give it the model, and we're going to select the handwritten image 5. That's the one we're going to attack. So put in 5, checkpoint path, and then we're going to specify 3 is the output layer, and we're going to put a bias of 1,000. It's rather noisy, but it'll work for this. So we'll run that attack. Now let's see what the accuracy of the model is now. So let's print the accuracy. A second, let's run that. And then also we're going to get the predictions of the model itself. And then in addition to seeing the accuracy, we want to see all the outputs. We should not see any 5s. We should see everything else but 5s because we selected the neuron that mapped to 5. All right, let's fix my typos. Let's see. Oh, I see. Yep. And there, dir name, not name. Should be it. Let's run this. You can see the output. Those are all the labels the model is predicting. Let's scroll all the way to the top. You can see the model has an accuracy that's a little bit lower than our original one, but we would expect that because it's a Trojan model. Now let's look through our output and see if there are any 5s. Because of our bias in there, there should be not any 5s, and I don't see any. So you can see right here are a couple of articles that go more into the math and details of how to implement this attack. I'll put those in the notes. But yeah, this is a very simple single bias Trojan that we've implemented into our model. If you are interested in seeing more of these attacks, subscribe to the channel, and then in the comments put a AI attack that you would like to see a tutorial on. Thanks.